So welcome to today's lesson. We're going to begin mathematical induction. So this is lecture 18. If you need other lecture slides, they are in the Telegram group. I shared to everyone. But for these, I think you are the only ones who are going to be having these lectures. So so today we're going to be looking at the definition of mathematical induction. We're going to check we're going to look at what mathematical induction is, and we'll also look at the rules of mathematical induction. We'll also look at the truthfulness of inequalities, and also the extended principle of mathematical induction. So we can quickly begin. So what is mathematical induction? So mathematical induction is simply just a method of proof, and it is mostly used to establish the validity of statements that are given in terms of natural numbers. So mathematical induction is simply just okay. There's a hand already. Let me just see what this person wants. Okay. Yes, Chanda. Okay, Chanda, you can speak. You can go on. What's the question? All right. Seems he doesn't, I don't know if he or she doesn't want to respond. So what we're going to do is, let's just proceed. So we're talking about mathematical induction. Mathematical induction is simply just a method that is normally used to prove mathematical statements, the validity of statements in mathematics. So let us look at some rules that are involved when solving questions about mathematical induction. So the first one, okay, let me just do this. Okay, the rules are we have the rules which are called steps. So the first step that is used to prove the validity of questions in mathematical induction, you first have to test whether the given expression, for instance, if you've been given, let's say n, maybe 2n minus 1 is equal to maybe n squared, something like this. Yeah, something like this. Though I'm not really sure if this is correct, but it has to be proven by mathematical induction to check whether it's correct or wrong. So if let's say the first step, you have to test whether the given expression is true for all values. I mean, for the first value, meaning the initial value of n. So the initial value of n can be any number in a given set of numbers. So in most cases, when we're dealing with mathematical induction, we deal with natural numbers. Yeah. Hello? I'm hearing some noise. Let me just mute everyone. Okay. All right. So when we're dealing with mathematical induction, in most cases, we deal with natural numbers. So the natural numbers are counting numbers just starting from 1 to accounting numbers starting from 1 going up. So when you say here the value of n is supposed to be a natural number, you simply mean you get any number starting from 1 going up. All right, so let's quickly move on. The next step that is used to prove for mathematical induction, you first check if it has accepted, meaning if this was our statement, then the question was telling us to say for all natural numbers, It means that our first natural number, meaning our initial natural number, is going to be 1. Meaning the first thing that we need to do on this step, on this first step, we need to test for P of 1. So when we say P of 1, we simply mean you try to put 1 while there is n here. So you put 1 while there is n. You see if what you're going to get on the left-hand side will be equal to what you get on the right-hand side. Okay, so let's move on to the next step. So step 2 says if the given expression is true for P of n initial, then assume that it is also true for P of k. So meaning if you have been given a question or an expression, maybe for instance, the one that I wrote here, the one which I wrote to say maybe n squared is equal to 2n maybe minus 1. So if you find that it is valid, if you put a 1 this side while there's n, you also put 1 on the other side while there's n. Then you discover to say you find something, maybe something that looks like this. Maybe you find your answer to be this side being equal to that side. It simply means that it is true for this it is true for this P of n initial. So meaning if it is true for this, it simply means that you can go further on the second step and assume to say it is also true for P of n. I mean for P of k. In other words, they are trying to tell you to say you also find P of k. Meaning in this expression which you've been given there, where there is n, you are going to put k. So you're going to have something like this. You're going to get something like that. Oh, sorry, here then you put k while there's n. So that is going to be your next step. And then we move on to the third step, which is usually the last step. So on the last step, if the given expression is true for P of n of 0, or the initial value of n, you can also make another assumption to say it is also true for P of k plus 1. Why do we use k plus 1? If the natural numbers are given as 1, 2, 3, 4, going up, we know to say natural numbers are just counting numbers starting from 1 going up. So if you've been given these numbers here, and then if we know to say this is a set of natural numbers, and then if maybe our n initial was 1, and then our next number there, if the initial value of n is 1, our next number there is 2, our next number there is 3, it simply means to say the difference between the first number and the second number there is just 1. So meaning if I have my first number which is equal to k, if my first number is equal to k, if I want to find the next number there, I'm going to have this k plus 1. In other words, what I'm trying to say is if you have your first value there is 1, if you want to find the next value in this sequence there, you say 1 plus 1, you get 2. 2 plus 1, you get 3. 3 plus 1, you get 4. This is the reason why we use k plus 1 as our next value of n. So if your assumption here, if n of initial value of n, if p of the initial value of n is true, it simply means that p of k will also be true. Even p of k plus 1 should also be proven to be true. All right, so let's quickly proceed. We look at the next values. Let's quickly look at the next values. Okay, so we have, okay, let's take a look at examples. Maybe the examples will make you at least understand things clearly and properly. Okay. All right, so the first example, yeah, so what has just come down there is just it's just a conclusion. to say then P of n is true for all natural numbers. So this P of n is only true for all natural numbers if it passes this, it also passes that, and then finally passes that condition. You test it first by putting or by using n is equal to 1, meaning in that given expression that will be given either on your exam or in that given formula, you first try to put where there's n, you put 1, and see if you are going to get the value this side to be the same as the value on that other side. If you get the value this side being equal to the right hand side, the left hand side being equal to the right hand side, then that statement will be true, meaning it has passed that first step. And then the second step here, you just make an assumption to say if the first step here is true, then the second step there, which is P of k, is also going to be true, meaning your value of n there will just be equal to k, meaning in that given expression that you'll be given, you have to replace where there is n, you put k, and then after assuming that it is true for this, make another assumption to say then it is also true for that part, which is P of k plus 1, meaning in this case your n will now be equal to k plus 1. So meaning wherever there is n in your expression, you put k plus 1. Okay, let's look at an example. We have this example there. So this is just your question 1 in tutorial sheet 6. I decided to use questions from the tutorial sheet as an example because I know to say it's really going to help you. So let's look at the first part there. So when you look at the first question here, we've been given to say prove by mathematical induction that for all positive integers n, this is going to be true. So we know to say our first value there is 1, second 3, third 5, then we go on to infinity. And then the formula that satisfies all these conditions there is just this one. So now to prove that this formula is true for all values of n, meaning for all natural numbers, we first take our initial natural number, our first natural number. So our first natural number is n, which is equal to 1. So our first natural number that we have is 1. So I'm pretty sure maybe are you all able to see my red ink there on blue? If you are able to see, then we can proceed. Okay, so n is equal to 1. So n is equal to 1. This one is my first natural number, which I have. So I have to test now. So how do I test? I'm going to find P of 1 in this formula. So what is P of 1? Or what does this mean? I'm going to put where there is n in this expression, I'm going to be putting 1. So I'll put 1 where there's n. So I'm going to have this being equal to 1 squared. So we're going to have this 2 times 1 will get 1. 2 times 1 will get 2. And then minus 1, we're going to get 1. And then this side, we know to say 1 squared is just equal to 1. So since 1 is equal to 1, and this expression here is true, it means that this given formula is true for the first value of n. So when you see something like P of n initial, it simply just tells us to say this n initial is just the short form of the first value that we need to test with. Okay, so we know to say it is true for P of 1. So we have found that this is true for P of 1. So I'm going to write it there. So I'm just going to write it to say this is true for P of 1. Let us now find this when the value of n is k. So meaning we're finding P of k. So in P of k, we know to say n is just going to be equal to k. So meaning where there is, let me just write it this way. Okay, so meaning while there is n in this expression, I'm going to put k. So I'm going to have 1 plus 3 plus 5. Then I'll write my 3 dots. Then I have, oh, there's also a plus there. Then I have plus. Then I'll write this part, but where there's n, I'll be putting k. I'm going to have 2k minus 1 being equal to k squared. So from there, we also now need uh, this is just an assumption that if the first test there which we made was true, so we found that 1 was equal to 1, which is mathematically true. So if this is true, we now assume to say it is also true for P of k, meaning n is now going to be equal to k. So meaning while there is n in this expression, we're going to put k. So we move on to the next step. So this was our step 1. So our step 2 was for us to prove for n is equal to k. So let us now test this also as in our step 3. So meaning we're going to find now for the next value of n in the in the set of natural numbers, and then the next value of n in the set of natural numbers is just found by k plus 1. So meaning we are going to find p of k plus 1. How is that going to be? So meaning the value of n in this p of k plus 1, the value of n is just going to be equal to k plus 1. So in this expression now, we're going to have our 1 there plus 3. So I'll write plus dots. So it doesn't matter whether I end with 5 or 3. I know to say it's guarded by this by the formula 2k. So I'll write my plus there now, and then I'll have my 2k minus 1. I'll write it there, and then I'll say plus. So what I've written is just from 1 up to this part here. From 1 up to this part. So now I need also to write this. I mean to write my next value in this sequence. So I've ended at 2k minus 1. Let me now write my next value in the sequence. So the next value in the sequence is just going to be equal to 2. While there is k, I'm going to put k plus 1. While there is k, I'm going to put k plus 1. And then where there is k, I'm going to put k plus 1. So in this expression, which one? In this expression there, where there is k, I'll put k, I mean, where there is n, I'll put k plus 1. And then I'm going to have minus 1 there. So this is just going to be equal to this part. So this part, while there is n, I'm putting k plus 1. So I'll do this, and then this is going to be squared. So now, I'm going to take the left-hand side. So I want you to look at this part there, just this part there. When you look at this part here, this first part, maybe I also include the 5 there so that you don't get lost. Yes. So look at this part here. When you look at this part, doesn't it look the same as this part? It does. So when you look at this part which I've put in brackets, it just looks the same as that part. So if I take my left-hand side, where there is this, I'll say this is equal to, and then where there is this part in this expression, I'm going to put k squared. While there is this expression, in this expression, I'm going to put k squared. So I'll write this part, instead of writing all these things, I'll just write k squared, because I know that this expression is just equal to k squared. So I'll write k squared there. I've seen there's a hand there. Let me just write this. And then I have this, which is 2k plus 1. Okay, so I have that. Let me just attend to this person. Kindly repeat the third step. All right. So the third step here is where there is n. When you look at this part here, where there is n, I'm putting k plus 1. So my value of n is k plus 1. So in this expression, where there is n, I just had to put k plus 1. So in this whole expression here, where there is n, I put k plus 1. So I first wrote my first sequences there. I first wrote my first sequence. I wrote it there. I just brought it there. So after writing my first sequence there, I did what? I wrote the next number in the sequence. So the next number in the sequence, if I have these natural numbers, 1, 2, 3 going up. If my first number is 1, my second number is going to be 1 plus 1, which is going to give me 2. My third number is going to be 2 plus 1, which is going to give me 3. So meaning if this is my sequence there, my next number, instead of having just k, is going to have k plus 1. So this is the reason why there's n, I'm putting k plus 1. So while there's n, I put k plus 1 in this expression. So after putting that, if you look at this part there, it is just similar to that. Actually, it's not similar, but it is exactly the same. So if this whole part here is equal to k squared, don't you think that where there is this part in this expression, I can put k squared? So this is what I just did. Where there is this part, so while there is this part I've put in brackets, this part in this expression, this whole expression, I had to put k squared. So I put k squared there, and then I wrote my plus. This is the plus there, and then I said this 2 is that 2, and then yes, let me use the pointer. This plus here is this plus. This 2 is that 2. This k plus 1 is that k plus 1. And then I'll write my minus 1 there. Minus 1. So I'll leave this part. I want to prove that this part is equal to, this right hand side. So k plus, let me just write it here so that at least you should be seeing what I'm writing. So my right hand side is just equal to k plus 1 squared. This is my right hand side. So if this is my right hand side, this can also be written as, when I simplify this, I'm going to have k squared. When I expand that, k squared plus 2k plus 1. This is what I'm going to have. And then here, what I'm going to have is this part here, I replaced it with k squared, which is that k squared. I had to put k squared there. And then these 2k plus 1 is this part there. And then this negative 1 is that negative 1. So this whole part is called my left hand side. So my left hand side, I want my left hand side to look as to look exactly the same as my right hand side. If they are different, then the formula is wrong. But if they are same, it means that the formula is going to be true for all the values of n. So let me simplify this. So I'm going to have, this is going to be k squared. So when I simplify this, I'm going to have something like plus 2k and then plus 2 minus 1. So this is just simply going to give me k squared and then plus 2k, and then 2 minus 1 there will give me positive 1. So when you look at this, isn't it just the same as this expression there? So this expression there, when you look at properly, is indeed just the same as this one. They are just the same. Let me just write this one properly. They are just the same. So now, if they are the same, we can now conclude to say, since we can now say since the right hand side is equal to the left hand side, then I can't just write it here, but you can write it somewhere. You can say then what's this? Then the value, then the formula 2n minus 1 is equal to n squared is valid for all positive integers of n. I repeat again. I repeat. So since the right hand side is equal to the left hand side, then this formula 2n minus 1 is equal to n squared is valid for all positive integers n, or for all positive integers of n. All right. Okay. So I hope we have no questions here. If there is any question, you can ask, please, before we move on to the next question. All right. So I hope there are no questions. We proceed. Okay, Harrington has a question. So you can speak, Harrington. Harrington, you can speak. Okay.
Sir, can you please just repeat your statement?
Or the statement?
The right hand side.
Okay. So since the statement is that since the right hand side is equal to the left hand side, if you want, you can say since the left hand side is equal to the right hand side, then this formula here, which is 2n minus 1 is equal to n squared, is valid for all positive integers of n. Since the right hand side is equal to the left hand side, then this formula, which is 2n minus 1 is equal to n squared, is valid for all positive integers n. All right, so I think we can now proceed. So the next question, you also do it in a similar manner. Almost all the steps that we have done here. So on this question, I'm going to be a little bit fast because we have done the first one step by step. So the first thing that you need to test this formula that you've been given with P of 1. So we try to put we try to put 1 where there is a P there. So when we're testing for P of 1, it means that whenever there is n there, we're going to be putting 1. So we put 1 where there is n. So when we put 1 where there is n, we're going to have 1 times 1 plus 1 there, we get 2. So it's going to give us 1 over 2 this side. So let us also try to check if it's going to give us the same on the right hand side. So we put 1 where there's n on the right hand side. So we have 1 over, the denominator there will just be 1 plus 1. So we get 1 over 2. So when you look at these two numbers on the left and on the right hand side, when you look at them properly, you discover that they are the same. So if they are the same, this simply means that the expression there is going to be true. Okay, there's a hand. Are you going to send the video of the lecture because I'm facing network? Oh yes, I'm going to send the. I'm actually recording. Yesterday, the reason why I couldn't send the video of what we were learning yesterday, it's because the time I was teaching, I was in a place where network was a challenge. So the video wasn't that clear. It wasn't. It was cutting. It was cutting every after just a few minutes. So I couldn't send it. But this one, I'm going to send it. We're actually even remaining with 10 minutes. So let me just explain this point so that we see what we can do next. Yeah, if time is going to be, if we won't manage to finish this lecture, maybe I'm going to send another link which you are going to join, and then we finish up this slide so that next time at least we do something else. But it's a short slide about just 4 pages. All right, so we have found that this is true because what we found here is equal to what we found on the right hand side. So let us now, if this is true for this, for n0, if this is true for p of 1, then let us also assume that it is also true for p of k. So we make an assumption that it is also true for p of k. So if it is true for p of k, it means that where there is n in that expression, we're going to put k. So we're going to have something like this, 1 over k, and then we open the bracket, k plus 1, like that. Then we also write the same on this other part. So meaning we're going to have k, where there's n, we put k. So we're going to have k plus 1 this side. So when you do this, remember there are numbers this side. There are numbers which are these numbers there. So we now move on to the next step where we're going to make another assumption that okay, so we make an assumption, we make another assumption that this is also going to be true for, this is also going to be true for n, this is also going to be true for, sorry, yeah, for n is equal to k plus 1. So we also make an assumption that this is going to be true for n is equal to k plus 1. So this is what we're going to have. So if this is true now, it means that our value of n there will just simply be equal to k plus 1. So meaning what there is n in this expression, I'm going to be putting k plus 1. Okay, so we proceed. While there is n, I'll put k plus 1. So I'm going to have, so instead of writing all this, let me just write the first term so that at least we reserve some time. So the first term is 1.2 there, 1 times 2. Okay, so say plus dot dot dot, and then I'll write this term, I'll write that term, which is 1 over k. Then we have k plus 1. And then we have plus, so meaning our next term there, where there is k, I'm going to be putting k plus 1. So I'm going to have 1 over, where there is k, I'll put k plus 1. Rather, where there is n, I'll put k plus 1. And then in these brackets where there is k again, I'm going to put k plus 1. So when I put k plus 1 there, I'm going to have k plus 1 plus 1. So when I have something like this, I can just write k plus 2. Yeah, instead of writing k plus 1, let me just write k plus 2 so that it is at least shortened. Okay. So this is equal to, where there is n, I'm putting k plus 1 over, so I have k plus 1 plus 1, which is just the same as k plus 2. Which is just the same as k plus 2. So now here where I've reached, I have to prove that this part, this side, is equal to that part. And how do I do that? So I'll take the left-hand side. So the left-hand side is this part here. So this part, when you look at it properly, when you look at this part there, starting from here, going this side, this is just the same as starting from this side, this part, going that side. So I'm going to get, so where there is this part there, I'm going to replace with that, because I know that this part there going this side is just equal to k over k plus 1. So I'll put k over k plus 1 on this position, k over k plus 1, and then I'm going to have my 1 over k plus 1, and then we have k plus 2. So from there, you can now say this is equal to the left-hand side. So I want to show that what I've written here is equal to the right-hand side. So this is just my left-hand side. So this should be proven now to say it's equal to that. So how do we do that now? Let me just demarcate. So how do I do that? Okay, how do I do that? So here the common denominator is going to be equal to, I know that there's k plus 1, there's k plus 1 there. So my common denominator is just going to be equal to k plus 1 and k plus 2. So this is going to be my common denominator. And then when I cross mod, when I say this k plus 1 into that, I'm just going to get k plus 2 times k. So I'm solving for my left hand side. And then when I say this into that, I'm going to get 1 times 1, meaning I'm just going to have, yes, I'm going to have plus 1 this time. So when you simplify this on top there, you get k squared plus 2k plus 1. So what you've gotten there on top is a quadratic equation. So that quadratic equation, you have to factorize it. So when you factorize the quadratic equation, that quadratic equation, you get factors like, yes, so when you factorize that quadratic equation, you get, okay, let's factorize it here. We have k squared, though we don't have enough time, okay? You have k squared plus k plus k plus 1. So we factorize, we have k plus 1 plus 1, k plus 1 there. When you factorize this, so what you're going to do is you're going to put these together. Then what is common there, k plus 1, you also put them in brackets. So on top there, we have k plus 1, another k plus 1. That's what we have on top. Then everything divided by k plus 1, and then k. So when this link finishes, when time elapses, I'm going to send another link to the group. You should join quickly so that we proceed. Then we have k plus 2 there. So as you can see here, this can cancel with that part. So meaning we're going to remain with k plus 1 over k plus 2. So when you have this k plus 1 over k plus 2, you have k plus 1 over k plus 2. So this is your left hand side. So your left hand side is equal to this. And then when you look at your right hand side, it's just this part. So when you look at your right hand side, it is just the same as the left hand side. Hence, you have proved that this formula is valid for all values of n, for all positive values of n. So this is how